Right, welcome to Unit 3. In Unit 3, we're going to be talking about three different parts. It will be having something to do with gravitational, something to do with electric, and something to do with magnetic. And we're going to be talking about field. Field is a word that is quite new. I think we're used to the word force. Every time when there is a force, there is going to be a force field. Okay, I think gravity is probably the easiest one to grasp. We know that if this is Earth and this is an object, we know that there's going to be a force of gravity pulling it down. If I have an object and this object is experiencing the gravitational field, okay, say if I have an object and it's right here, it's going to experience the force field to cause it to move a certain way, and that's what a field is. And so basically, scientists have been using gravitational attractions to study the universe, especially predicting planetary motion like Neptune's and how it affects Uranus and other planets. They actually also use the force field to predict what the motion should be, and that's how they found Pluto. Okay, they're indirectly saying, okay, outside of Neptune, there must be something else out there because Neptune is moving a certain way that we can't account for the real force. There must be another large object that is on the other side causing it to move, and that's how they use the force field to study. Okay, and Isaac Newton is probably one of the most famous person to be talking about force field, and I'm going to tie this together and talk a bit about that. Okay, if I talk about force of gravity, I think if I ask you what is the equation to calculate force of gravity, you would be using m times g, where g is equals to 9.8 meters per second square. But I don't know if you remember the parameter that we gave you. It's like with an assumption that you're very close to Earth's surface. Okay, the reason for that is we're now telling you, you know what? Fg, force of gravity, actually has another equation which you might not have heard of it in grade 11. Okay, is g m1 m2 over r squared. And this is called the Newton's law of gravitation. And basically how it goes is there's telling you that whenever I have two objects, okay, object 1 and object 2. Okay, if I know the mass of each in kilogram, and if I know the distance, the key thing is the distance is measured from the center of the object. So center of object. And what you would realize is that if I plug it into this equation, I can actually calculate Fg. So how did it go from this big humongous equation to this smaller one that is m times g? Okay, if I think of an object, okay, if this is Earth, whenever I'm talking about Fg, it's basically talking about Earth with another object. If I call this M1 and if I call this M2, the two objects, right? The distance between the center of the object, it's actually the radius of the Earth. Do you see how like they're touching each other, but we're not talking about the distance between the object. We're talking about the distance between the center of the object, with Earth being so massive, with whatever the object, a cup on Earth, the distance we're going to use is the radius of the Earth. And if we plug it back into this equation, so Fg is g, this capital G is actually a constant. We're going to talk about what that number is. Okay, the mass of the object, which is m1, the second mass is mass of the Earth, okay, divided by the radius of the Earth square. When they do the calculations, what they have done is, if we take all these guys and we multiplied it out, it actually worked out to be 9.8. And that's why this is a short form. That's why Fg is m times 9.8. M being the object that is on the Earth's surface. Okay, and that's where it came about. And so they gave you this equation, so I'm going to ask you to highlight it. Fg is g m1 m2 over r squared. This equation is called the universal law of gravitation. And this capital G is called a gravitational constant, and it is this value. Okay, 6.67 times 10 to the negative 11 newtons meter square per kilogram square. Do you see where that unit came from? If I quickly rearrange this equation, Fg is g m1 m2 over r squared. If I rearrange it for g, it will be Fg times r squared divided by m1 m2. And if I look at the unit, Fg is in Newton, r squared is in meter square, and divided by kilogram square. That's where this unit came from. So just from rearranging the equation for g. And another key thing we've already stressed, r is the distance between the center of the object. If the object is not very big, we if I have a pencil and a cup, it's not that big, we don't count the radius. But if I'm talking about really big planetary motion, you have to count the radius of the object to be able to account for the center distance. So it's measuring meters. M1, M2 is measuring kilograms. Okay, let's do a simple example first. Okay, so question 1. The center of the two uniformly dense spheres are separated by 50 centimeters. Each spheres have a mass of 2. Calculate the gravitational force of attraction between the two spheres. Okay, so I know the distance, radius, is 0.500 meters. Each sphere, so both M1 and M2 are 2, and they want you to find Fg. So Fg is gm1m2 over r squared. G is a constant, 6.67 times 10 to the negative 11. M1, M2, they're both 2, divided by r squared, so 0.5 to the square. Punch it in your calculator, 6.67. My calculator is EXP. I don't know if you remember how to punch it in, but we would replace this by the EXP or the EE button. Some of you have the times 10 to the X button. Okay, so I'm going to punch EE, negative 11 times 2 square divided by 0.5 square. So my answer worked out to be 1.07 times 10 to the negative 9. It is a force, so it's measured in newtons. And yeah, and this one is not down actually, because the force of attraction is between the object. I'm not talking about the Fg going from the earth, right? So this one, it could be a left or a right or whatever, so I'm not going to write the equation down. Okay, so the next question. Bigger numbers, planetary. Asteroid A has a mass of 1 times 10 to the 20 kilogram. Asteroid B has a mass of twice the mass, and it is 50 million okay, highlight this one, 50 million kilometers, so it's 5 times 10 to the 10 meters from asteroid A. Asteroid C has a mass of 4 times 10 to the 20, and it is 2.5 times 10 to the from A. Determine the net force on asteroid A from asteroid B and C. Okay, so asteroid A is right here. Okay, if I have asteroid A right here, what is the force that asteroid A is going to feel between A and B? So understand that there is a force of attraction for gravity, right? So if A is being attracted to B and A is also attracted to C, I wanted to find the net force on A. So what is A feeling the whole time? Okay, I know that between A and B, do you agree that I'm going to feel a force that is going upwards by object B? Okay, I'm going to label the force between A and B is going to pull outwards, right? Because A is feeling the gravitational pull from B. Okay, and then what's happening between object A and C? Okay, they're attracting, so meaning A is also going to feel another force that is pulling between A and C. So C is going to want to pull A towards the right, and B is going to want to pull A upwards. Okay, so separately calculate what each of them are, and I would like to find the net force. Okay, if I take a look at it, what is the overall net force? Which way will it go? I don't know if you're seeing that, but in general, the general direction would be somewhere that way. Do you see that? I'm being pulled upward as well as to the right. The overall force should be going on an angle. Okay, so let's work out what each of them are. Okay, so FAB. I'm going to do FAB first. Force of gravity between object A and B. GMA MB divided by the radius between A and B square. So I'm just using the same equation. I just put a little subscript so that I use the right number. G 6.67 times 10 to the negative 11. That's a constant. It doesn't change. It's always that number. Okay. A, mass of A is 1 times 10 to the 20. Mass of B is 2 times 10 to the 20 divided by the distance between A and B, which is 5 times 10 to the 10 square. Don't forget the square. That's a common mistake. So 6.67 E negative 11 times 1 E20 times 2 E20 divided by 5 E10 to the square. Okay, so 5.336 times 10 to the 6, 7, 8. So I got this. And then you do the same thing. And this one, I do know the direction is going upwards. Well, north, sorry. I didn't see it. It should be north. I see this. So this is north. Okay, second is now FAC. So I'm now dealing with mass from A and the mass from C divided by the distance between A and C to the square. So 6.67 times 10 to the negative 11, mass of A, mass of C, all divided by the distance, which is 2.5 times 10 to the 10 square times 1E20 times 4E20 divided by 2.5 E10 square. 4.2688 times 10 to the 9 Newton. And this is going to the east. So if I have a force that's going north and if I have a force that's going east and I need the net force, you can just go, this is the north and this is the east. East is bigger. So 4.2688 to the 9. Sorry, running out of room. 5.336 times 10 to the 8. This is Newton. I'm so sorry. I don't know why I put meters. Newton. Then the net force is starting point to ending point. This is the overall net force. Now remember vector additions. When I find the net force, I just add the two vectors together. So this is a right angle triangle. So F net is going to be the Pythagorean of it. So I'm going to do the Pythagorean theorem and work out my F nets. Take the root. So it's 4.3. So 2 sig dig is what I'm keeping. 4.3 times 10 to the 9 newtons, and then I need the angle. So this angle I'm going to be looking for is the one that is at the bottom. So tangent of theta is 4.2688 times 10 to the 9 divided by 5.336 times 10 to the 8. find the angle theta. Shift tangent. So I got something like an 83 degrees. So north, 83 degrees east. Okay, and now I'm going to suggest you to pause the video and do part B on your own. We're trying to find the net force on B. So what is block B going to feel in terms of the force? The concept is the same. You find the separate force vector that is acting on B from A and C, and then you use vector and figure out what is the overall net force. So pause the video and okay, so now focusing on the object B, I need to know what are the forces that's acting on them. So separately, we're going to calculate the force. Force object B is going to feel a pull, a gravitational pull between the force of AB, which we calculated from the other side already. So we're going to reuse that number. But then at the same time, it is also going to feel a pull. I'm going to change colors, sorry. I'm going to feel another pull that is from right here between object B and C. So we're going to calculate that separately. So from the previous question, we already calculate that the force between A and B, but this time it's going to the south, right? So I'm just going to go back to the question. FAB, I'm not going to redo the math, 5.336 times 10 to the 8 Newton going to the south. So that's done already. So then separately, I'm going to calculate what is the force, so FG in between B and C. Okay, so to calculate that, I'm going to use back the same equation. F equals G M1 M2 over R squared. So M1 is object B, M2 is object C, and then it's the distance between B and C to the square. So 6.67 times 10 to the negative 11, that's a constant. Mass of B is 2 times 10 to the 20. Mass of C is 4 times 10 to the 20, all divided by. So here is the thing. We actually don't have that, but we can calculate it because we know the two sides, right? We know, so what we have a triangle, and if I already know that between A and B, the distance is 5 times 10 to the 10. And then the distance between C and A, it's 2.5 times 10 to the 10. Right angle triangle, we can quickly work out what the distance between B and C is. So I'm not going to write them all out, but the root of the square of the other two. I'm not writing out the whole Pythagorean theorem here. I just want to save space. Okay, so 5e10 square plus 2.5e10 equal, take the root. So this is 5 times 10 to the distance to be between object B and C to be 5.59 times 10 to the 10. So I'm going to plug this in, 5.59 times 10 to the 10 to the square, right? Don't forget it's R square. So now plunge everything in. So 6.67 e or negative 11 times 2e20 times 4e20 divided by that to the square. I got 1.7 times 10 to the, it's a huge number, I'm going to say 1.71 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 to the 9 newtons. Okay, the direction, I need to find this angle. So this angle theta, so it's tangent of 2.5 over 5. You can put times 10 to the 10, but they would cancel. So I got the angle theta to be 27 degrees. So this would be south 27 degrees east. Okay, so now I got two vectors. One that's going south, the other one that's going south 27 east. So I'm going to have to quote unquote vector addition and add them together. So starting point here, I got something that's going south. These numbers are really big, so you got to be careful. I'm running out of room. 10 to the 8th Newton. And then from there, the other vector, then it keeps going south 27 east. So this is 27 degrees, and this is 1.71 times 10 to the 9 Newton. So the overall resultant is starting to ending point, and that's what I need. These questions are not hard, but they're easy to make mistake because, the little square, all the exponents and stuff, they're really big number. All right, so I need to find F net. This is a cosine law question, so I'm going to have to find this angle because the bottom angle is 27. So from a straight line, 180 minus 27, that gives me 153 degrees inside the triangle. So F net square is going to be the cosine law times 10 to the 9 square minus 2b c cos of 153. So many numbers, so many decimals. So let's get to it. So I got 5.336 E8 to the square, adding 1.17 E9 to the square minus 2 times and take the root. Oh, you double check my answers. I don't want to redo this, but I got 1.6 times 10 to the 5, 6, 7, 8, 9 newtons. I did my answer twice. I got 1.66. 1.663. So if I need 2 sig-digs, I have to keep it as 1.7. And then finally, I need to find the angle. So the angle that I need to find would be up here. Angle theta is opposite to 1.17. So sine of theta over 1.17 times 10 to the 9, it's going to equals to the sine of 153 all divided by 1.7 times 10 to the 9, because that's what we found in here. So cross multiply, angle theta would work out to be, so sine of 153 I got 19 degrees, so the angle is south 90 degrees to the east. Okay, as I said, you find the force and then you add the vectors together like vector components. That's what this question is. Continuing on the lesson, the gravitational force Fg is always attractive, and that's why when we did the example just now, if I'm looking at object A, the force is always pointing toward B because that's the attraction force is going to pull them together. And the two gravitational force are action and reaction force, so it especially easily explaining using the planetary motions, right? You know how like we got a satellite that's orbiting around, say, Earth, right? One thing you need to understand, okay, let's not say satellite, like a moon, right? I know that the moon is pulling on the Earth and the Earth is pulling on the moon at the same time. It's always a third law question, and that's why you would have tide, right? Tide is the effect of the moon on the Earth. The Earth is keeping the moon in an orbit. That's the action force. The reaction force, moon is totally pulling the exact same force towards itself, right? So another thing you need to understand is that this law follows this thing called the inverse square law. Okay, going back to the equation, Fg is gm1m2 over r squared. If I double the distance, what I have done is I've actually make it 1 over 2 square weaker, meaning it's going to be the quarter of the original size. So that's why it's inverse. Increasing radius, make force smaller because I'm dividing it by a bigger number, and then it's the square of it. Okay, moving on to g, okay, lowercase g. We already talked about near the Earth's surface is 9.8. And how do you calculate g? Is you would use the equation and just solve for what g is. Okay, which would be at the bottom here, I think. Okay, so how do you calculate g? So g is actually called the gravitational field strength. Okay, and so to calculate g, I know that F equals g m1 m2 over r squared. I also know that Fg is equals to m times g. This m is talking about the object that is near the Earth's surface, or say on the Earth. Okay, if I draw a picture, if this is Earth, if I have an object, okay, I call this m. So this m is this. This is the mass of the Earth. This m is also that m. So that means if I want to work out g, I can equate these two equations. I know g m1 m2 over r squared is equals to m times g. But as we just now already established, this is the mass of the object on the planet. This is also the mass of the object on the planet. They're the same. So that means I can cancel them. So the equation to work out what g is g m2. The m2 is the mass of the Earth, or whatever the planet is, over r, which is the distance between the two objects. And if it's totally touching, we talked about that the distance really means the radius of the Earth. Okay, and that's what g is. And so if the object is any further away, say if it's whatever distance away, my radius would change. So that talking about the altitude, do you see how the field strength g will decrease the further you go away from the Earth? Okay, I would like you to highlight this equation. Okay, so the equation for g. Okay, Henry Cavendish. I need you to know that he's the person who was able to calculate the Earth mass. Okay, he's using the equipment right here that he actually used to force tension to balance out the gravitational force. So he's the person who did work out what the gravitational constant is. I don't know how much you understand about math. So basically, when we talk about proportionality, we're basically talking about a ratio. And basically the g is the, you know how y equals mx plus b. It's the constant that makes it happen. Okay, and that's what the b is. Okay, so I'm done these examples. So now we're moving on. I already did this for you. This is how they calculated the force of gravity. So this is the equation that you could use for each of the planet. Okay, so question 3. Calculate gravitational field strength on the surface of Saturn, assuming that it's perfectly spherical and the radius is 6.03 times 10 to the 7. The mass of the Saturn is 5.69. So the only thing tricky that you need to know is, do you recognize what this word is? Gravitational field strength, meaning they would like you to find lowercase g. And the equation would be gm, and this time is Saturn, so I'm going to use a letter S, over the radius of the planet, which is also rs, and they gave it to you in the question. So 6.67 times 10 to the negative 11. Mass of the Saturn is 9.69 times 10 to the 26, all divided by the radius of Saturn, which is 6.03 times 10 to the 7 square. So 6.67 exp negative 11 times 5.69 exp 26 divided by 6.03 exponent 7 to the square. So it worked out to be 10.5 for, they're keeping 3 sigdics. The units for gravitational field strength, what is it? What's the unit? Yep, you can use meters per second square, or the other way, you know how Fg is m times g, right? So g is force over the mass. So the other unit you can use is Newton divided by kilogram. Both are the same because the base unit for Newton has the meters and kilogram and all those stuff, and that's where they came from.